All right, good afternoon. This is our screencast for Project 3. So Project 3 is going to look very similar to our Raoults Law problem set. So we're running out of time here at the end of the semester, so I don't anticipate Project 3 taking all that much time. But even though we don't have the time to work on a larger, more in-depth project, I at least want to get you looking at real data. Okay, and so for the Raoults Law problem set, what we did is for a given binary system, we predicted PXY phase diagrams using Raoults Law, and we compared to reference data from DDBST. Okay, and so PXY data is nice because for a system that obeys Raoults Law, we predict a straight line for our bubble line, right? A straight line connecting P1 sat to P2 sat. Okay, and so in a PXY phase diagram, it's really easy to identify deviations from Raoults Law. In terms of deviations from this linearity behavior in my bubble line, which we can attribute to intermolecular interactions, right? In terms of trying to gain an understanding of what's happening at a molecular level. When it comes to TXY phase diagram, you can still gain the same insight, it's just not quite as clear, right? And what I mean by that, or it's clear, right? It's just takes some thinking maybe, or maybe just getting used to looking at phase diagrams. And I only say that because, in a PXY phase diagram, Raoults Law would predict that my bubble line's a straight line, right? So in terms of looking for deviations from Raoults Law, it's just, does my bubble line deviate from linear behavior? In a TXY phase diagram, it's not quite the same, right? My bubble line's going to be predicted via Raoults Law as P is x1 P1 sat plus x2 P2 sat, okay? So now the issue in a TXY is for given x, temperature's changing, right? P1 sat and P2 sat are both functions of temperature. They're both going to have different temperature dependencies, right? So they're going to have, say, two Antoine equations with different sets of constants. So my bubble line isn't going to be linear. There's going to be some curvature for it as predicted by Raoults Law. So in terms of, just being able to look at, experimental data and say, hey, that has positive or negative deviations from Raoults Law, it's not quite going to be the case because Raoults Law would predict some curvature to my bubble line. Okay, and so what we're going to look at is we're going to do the same exercise as our Raoults Law problem set, only now we're going to look at isobaric data. So we're going to look at TXY phase diagrams. So you're going to look at the same component that you looked at in Project 1. Okay, only now instead of looking at PXY data, you're going to look at TXY data. Okay, so you're going to look at isobaric data. And so when we look at available or possible systems from DDBST, we're looking for, at a given pressure, here's T, X, and Y. Okay, so if TXY data is available for a given pressure for a binary system, you can look at it. So for that binary system, we're going to predict TXY phase diagram using Raoults Law. We're going to put our reference data on top of that graph, so we'll plot those as circles, and we're going to look at deviations of that actual data from Raoults Law in the TXY sense. All right, just to get an idea of what these things look like. And hopefully, since you looked at that same system for PXY, maybe you'll look at some of the same systems and see how things differ in going from PXY to TXY. Okay, so the goal here is really just to get you to look at some real data and try and look at and identify deviations from Raoults Law in a TXY phase diagram. And we'll also plot McCabe-Thiele Y versus X phase diagrams, and so you can look at deviations from Raoults Law in the McCabe-Thiele sense. So just as with the Raoults Law problem set and the others, so I have Matlab Code for you. So I have Matlab Code that will just update with our Antoine parameters, some names of our systems and plot titles, and reference data, and then it'll take care of the rest and generate the plots. And just like with the Raoults Law problem set, there won't really be an error analysis associated with this problem set. It's more so just going to be looking at the plots and making some observations. Okay, so without further ado, I'll take you through a couple of examples, and hopefully that'll give you what you need to be able to go on and take care of this on your own. All right, so right now it's the DDBST website I have open. Okay, but I'm going to go over to our team drive. Okay, so our team drive now has a new folder, Project 3. Okay, if I open up Project 3, the first thing I'll find are two sheets. These two sheets have been copied over from our Raoults Law problem set. So the first one is system assignment. Okay, and so it's the same sheet from before. So there's your name and then the system that I've assigned you. And so all I've done is I've taken all the systems available in the ddbst directory, removed the components that are either going to be solid at ambient conditions and the salts, and actually the incandescent gases like methane. So I've removed some of those special systems. And so I assigned one to each of you. Now there's at least one student where for the Raoults Law problem set, they said, hey, there's no complete PXY data sets available for my system, so I gave them another component to look at. All right, take a look at your system and see if there's TXY data and try and model up to 10 systems for your component. Right? I give 10 as an upper bounds. So I haven't gone through every single component and tried to look at how many sets of PXY and TXY data there are, right? But I give an upper bound of 10 of, don't go crazy, don't look at more than 10. Okay? But this is the same systems that are assigned to you from the first problem set, or from the Raoults Law problem set. And so hopefully there's data available for your system. And then again, I have a sheet available of, so this is tabulated Antoine parameters for all the components in that set. Okay, and so these are also taken from ddbst. And so now you'll need to be conscious of the temperature range. Okay, and so just try and do your best job. So if you look at the reference data, you should get an idea of what the temperature range of your system is. And so just make sure if more than one set of Antoine parameters are provided for your system, that you're using the appropriate ones. Okay, but if you've got everything there, believe even should have it set up so you can filter, based on which component you want. Okay, so that's the same as before. Okay, we're going to look at the free data again from ddbst. Okay, so this is the free VLE data, and so what I mean components, right? If you were assigned ethanol, right? What I'm referring to is you click on the little ethanol text, right? And you're going to look at binary systems from that header, right? Same sort of subtleties, exist here as it did for problem 1, right? ddbst just comes up with these lists based on all the systems with that common component. I don't know if it's a case, but if I were to click on ethanol hexene, let's see, you'd need to double check to see which they're calling component 1 and component 2. Right, so for instance, this is PXY data, but for this PXY data, hexene is actually component 1 and ethanol is component 2. Right, so try and keep track of that. Right? And, this system only has PXY data, so it's not one that we would look at. Okay, but I'll come back to downloading data in a second. Okay. The other thing you'll find in our team drive is our example folder. Okay, and if you go to example, there's 2 files there. Associated with generating TXY phase diagrams that are essentially just copied from the 324 text. So you'll want to download both of those. Okay, and so I just realized I didn't pack them all up into a single file like I did before, but that's okay. I'll show you exactly how to run them. Okay, so download both files to your computer. Okay, so now I'm going to go over to Matlab, and so I have this project 3. I have an example folder where I have both of those downloaded. Okay, this end file that's Raoult TXY generator, don't touch it. Right, you won't have to touch it. Don't touch it. Just leave it there. Okay, it's going to do the actual calculations for you, but don't touch it. Okay, what you are going to touch is, let me open up this file. Okay, and this is for hexane cyclohexane. This is going to generate a TXY and McCabe-Thiele diagram for the system hexane cyclohexane. I have to provide Antoine parameters, pressure, titles, okay, just like before. Here you just give the base of the name of the files, and I'll append it with McCabe-Thiele or XY, or TXY or XY for McCabe-Thiele, depending on the plot, and my reference data. Okay, and we'll go through an example of walking through setting it up. But once you have it set up, you should literally just have to click run, right? And I will get my TXY phase diagram and my McCabe-Thiele Y versus X plot. Where in this case, black is still going to be my bubble line, red is my dew line, lines are my Raoults Law predictions, and circles are my actual reference data. Okay. All right, but let's go through an example. Okay. So I'm going to go back over to my DDBST data, and let's just assume I had ethanol. Okay, so ethanol acetone seems like a great system. Okay, so let's look. Ethanol acetone, I'm looking for TXY data. Here I have some, right? At this pressure, we're given TXY data. Okay, and if I look, right, the only other data available there is PXY. So right, in this case, there's only one set of TXY data. But if there were multiple sets of TXY data, just choose one of them. If you want a rule of how you choose one, I don't know, choose the one that has the most data available. Okay, so let's look at this system. We're going to look at acetone's component 1, ethanol's component 2, and a pressure of 101.33 kilopascals. Okay, so acetone's going to be component 1. Okay, and if you want to call this ethanol acetone, acetone ethanol, it's fine. So I'm going to call this acetone ethanol. Okay. Oh. Okay, and when I do that, I need to, save a copy. So I'm going to do a file save as. I want to make sure I don't overwrite what I was doing before. Acetone ethanol TXY. So now I have acetone ethanol TXY. I still have my hexane, cyclohexane case there. Okay, but acetone ethanol. Acetone ethanol at 101.33. Acetone ethanol. Right. So hexane cyclohexane is a pretty ideal system, so our Raoults Law predictions or calculations were in really good agreement with the experiment. But hopefully this one is a little more exotic. Okay. So here's acetone. Okay. We're given two sets of Antoine parameters. If I looks like our temperature should be between 325 and 350 Kelvin. Okay, so if I go to acetone, okay, so this set of 325 and 350, we're kind of in the middle, in terms of what set of Antoine constants to use, right? So this is a case of just use your best judgment. Since we're kind of in the middle, it won't make a huge impact. At the end of the day, too, we're just trying to look at qualitative behavior. So I just copied and pasted there. Okay. Now for ethanol, this one looks like it should do. Just going to copy it, paste that there. Okay, that's good. Okay, now I just see my reference data. So I want you to copy the URL to kind of serve as your quick reference if you want to go back and check your data and where it come from. Delete the data in my matrix. Bam. Copy and paste. Okay. Get that lined up. Get these guys tabbed in. Okay. Save. And that should be it. Okay, so now if I click run, okay, whoa, cool. Okay, so first things first, I get, let's see, this would be my TXY phase diagram. So it looks like the endpoints approximately line up, so it doesn't look like things are off here. Okay, but maybe if I look at my McCabe-Tilly plot, okay, solid line again is going to be my Raoults Law prediction, and then here's my actual data. All right, so it's, the curvature is definitely different. All right, so if this is my bubble line, what does this predict? So if this is my bubble line predicted by Raoults Law, and my actual reference data, my bubble line is below my Raoults Law prediction. What does that mean? Right? Is this going to be a system in which it's the mixture is more or less volatile than my pure component? Right? And so if I have a liquid mixture of is my mixture going to be more or less volatile than a corresponding ideal solution? Right? And so if I have a mixture of 0.4 mole fracs, so this would be a liquid mixture. Right? The bubble point of that mixture is going to be at, this temperature, which is actually less than the bubble point of the corresponding, less than the bubble point temperature of the corresponding ideal solution. Right? So, what does that suggest? Okay, cool. And that's what it looks like on McCabe-Thiele. And you'll see the two plots are saved. So I get acetone ethanol TXY, acetone ethanol XY. If you open outside of Matlab, they should open up with your favorite figure or photo viewer, picture viewer. Okay, so that's acetone ethanol. Okay, let's look at another one. Let's see if our favorite system of acetone and chloroform has TXY data, right? So I know acetone chloroform should exhibit negative deviations from Raoults Law. Okay, so in fact we do. Okay, so let's look at this one. So I'm going to resave my file, save as. Okay, this is going to be acetone chloroform. Seems like I got a lot of Loros in there, but we'll just leave it. Okay, so we'll call this acetone chloroform. Okay, so component 1 still acetone. This is suggesting I spelled it differently. Acetone chloroform. Oh, I had an extra R in here. Okay, so just because I have a typo, let's just put the typo in there so they're correct or consistent. Okay, so first was acetone. Okay, so that one, well, let's see our range. So our range here, about 330 to 335. Okay, so if I go to acetone again, 330 to 335, right? So our second set of parameters should still be good. I go to chloroform. Okay, we're on the brink again. So I'm going to use our first set. Paste those in there. Okay. What's our pressure? 101.33 again. So this is acetone chloroform at 101.33. I'll call this acetone chloroform. Copy in the URL for my reference data. Bam. My reference data. Delete that. Copy and paste that set of reference data. Bam. Okay. I'm going to save it, and then I'm going to run it. Okay. Whoa. Okay. So now if I look at my TXY, okay, so one of the reasons for picking this is we know we're going to have negative deviations from Raoults Law, and acetone chloroform actually results in a maximum boiling azeotrope. Right? Acetone and chloroform are unique in that acetone can't hydrogen bond with itself. Right? It's a hydrogen bond acceptor, but not a donor. Chloroform can actually donate protons, so it's a weak proton donor or weak hydrogen bond donor. But not so much an acceptor, right? It can participate in halogen bonding. But when I mix the two of them together, they can associate with each other. Okay? And so now if I look at my TXY phase diagram here, if I have another liquid mixture, right, below my bubble line, a liquid mixture of 0.4 mole fracs, okay, what I find is that my ideal solution, right, has a lower bubble point temperature for that mixture than does my actual system, right? And so, what that would suggest is that it's, easier to boil, right, the ideal solution, as compared to my actual solution. Hence, we have stronger intermolecular interactions in solution. All right, cool. If I look at my McCabe-Thiele plot, this one's actually interesting, right, at my azeotropic system. All right, so I'm going to have an area in which I'm below and then above my y equals x line, right? Below then above is indication that I have a system with a maximum boiling azeotrope, so monoazeotropic, maximum boiling azeotrope. Okay, so if I close that, just to compare it, if I bring up acetone ethanol again, okay, and run that one more time, okay, so if I look at my TXY, so again, if I have a mole fraction of 0.4 mole fraction from my liquid phase below my bubble line here, okay, that mixture is going to have a bubble point temperature of this, all right? This is my actual system. My actual system is going to have a bubble point temperature of that, which is less than the corresponding ideal solution, all right? And so it's going to be easier, or my mixture is going to be more volatile than the corresponding ideal solution, which would result from unfavorable cross interactions, right? Cool. All right, and so I hope is that you go through and do a bunch of these. Okay, and again, the goal is just to get you looking at real data, right? So I want you to try and still keep trying to sharpen your skills in terms of getting an understanding or idea of when Raoults Law is applicable, when it's not, or just trying to acknowledge that there are limitations in the model. Right? Don't just use Raoults Law blindly. And then also in terms of these deviations from our ideal solution behavior, what do they look like in a TXY versus a PXY phase diagram, right? And PXY was nice because you could quickly identify positive or negative deviations from Raoults Law as deviations from that linear bubble line. It's not, it's still doable and straightforward and easy, for lack of a better word, in a TXY, but you might have to stop and think about it, which is what we want to do here. Okay, and then just as with all the other problem sets, once you're all done, you're going to create a folder. So if my system or my component was acetone or ethanol, I'd create an ethanol folder in our team drive and upload all of these files there. And just like before, we'll have a discussion. So you'll prepare a short report. Again, it's just going to be based on your observations. We'll have a discussion, which is just you sharing your observations with the rest of the class who have looked at different systems. Okay, and with that, I will stop this screencast. If you have any questions, please don't hesitate to